This video, we'll discuss section 15.4. This is over Green's theorem. The whole idea is the same concept that we're working on. We're given a particle that's moving through a path that's placed in a conservative, in a vector field. We're not going to work with conservatives here. These will be worked on non-conservative, and we'll deal with the conservative part here in a moment. But the first thing we're going to say is, what if the curve C that we're talking about is something called a simple closed curve? Okay, what simple means is it doesn't overlap. So if I have some curve, that's my curve, it doesn't overlap, right? If I took that away and I did maybe something like this, that is not a simple curve because it overlaps itself. Simple curves only, they don't overlap each other, right? That's a simple curve. This is not a simple curve. So simple curves don't overlap. The closed part just means literally that it's in closed region. So this is not a closed curve. But if I take that and I close it on itself, then it is a closed curve. It doesn't have to be a circle. It could be just any other weird shape. But to keep it within this type of problem, they have to be simple and closed, meaning they close a region on the inside and it doesn't overlap on itself. Okay, if that's the case, and it looks like this, right? This is our problem right here, P dx, Q dy. When it's over a closed symbol, and some of you guys are maybe like, what is that symbol there? This is what we put there. This is a simple closed curve, or a line integral over a simple closed curve. Green's theorem says, hey, if that is a simple closed curve, and it's traveled in a clockwise, counterclockwise direction, right? Counterclockwise, then we can use this. I can rewrite this whole integral as this integral. What's really nice here is notice this is partial of Q, partial P. If Q equals P, right? Right, this was from conservative, right? Conservative vector fields tells me that then what that means is when I subtract them, I get 0. So that'll mean that my integral is just 0. It's not a big deal if it's conservative. So that's how we do this. If it is a counterclockwise moving direction, simple closed curve. What's really nice is we're just going to have to draw a picture and then it's just set up. That's all it is. So this kind of talks through, like, if we're given a direction, we can do a dr. This is where this thing comes from, why it still work, right? It's the dot product of these two vectors right here, right? Or rather dr and this vector, I mean. So it's this vector dotted with those two. That's what this is talking about. We get that. So work looks like that. As long as it's a simple closed curve. This is the only time it's non-conservative vector fields. If the vector field is conservative, we're just going to get a 0. Because it's a closed curve. That makes sense, right? Conservative vector fields, independence of path. If I start at a point and I end at a point, I didn't go anywhere. So really the work done is 0. Because it was conservative. But we're dealing with them not being conservative. Let's get some examples. These are nice and easy to work with. So we have this. I have that triangle. We're going to draw. I would always recommend drawing these graphs. So we have a triangle from 0, 0. Here's 1, 1, 1, and 0, 1. So we have this triangle here. To use this theorem, we have to know that it's moving in this counterclockwise direction. We are walking around that. So we can set this up. So the integral over this closed region of x to the third dx plus xy dy. All right, this is going to be equal to some region R. We'll call it that for now. And then we just need the partial of q with respect to x. Okay, q being xy, so that's y. And then the partial of p with respect to y, it's going to be 0. So we get y minus 0 dA. And then now it just comes down to a double integral that we have to figure out. We use our shape here, and we have our double integral. We got our y, and then it doesn't really matter. I'm going to do what dy dx. The reason I did dy actually is from here. If I look at my y directions, I have a top curve and a minus and a bottom curve. We still have to do that. The bottom curve is right down the middle. That's y equals x. So we get y equals x to y equals 1. That's what we had there. And then remember, once we do that and define it that way, the x's can just be the numbers. So we get x equals to 1. I'm not going to evaluate the double integral because there's a whole section based on that. If you want to work it out and see how you do, it's 1/3. So that's how much work it would take to move that on that closed region, this triangle, in that vector field. All right, we'll get a few more. These are nice and straight, easy. I feel like these problems get easier as we go along. So this is P, this is Q. If I do partial of P, let's do Q first, since it's what we're used to. With respect to X, that's 0. The partial of P with respect to Y is also 0. This is a conservative vector field, so I'm just going to write F is conservative. And we would do this, use 15.2 method. If I could spell method. All right. We'll stop there for that one. Actually, we can answer this. This is equal to 0. It's a closed simple field. I think we're assuming it is. So it would be 0. Okay, we have another one here. We label P and Q. We also try to draw our shape. Okay, so this region, you guys have done so much of this in calculus. Y equals x. It's a little steeper than it should be, but there we go. And then x squared, this ends at 1. 1, we're so used to this curve. When we get that shape in there, we have to go around counterclockwise. So we're walking along this curve and back this way. And we want to know how much work would it take to walk along that curve in that vector field. So we take the partial of Q with respect to X. That's going to be 2y. I take the partial of P with respect to Y. Right, I get x squared. That's all I have there. So the work here, it's going to be over the region R, which we'll deal with. And it's going to be 2y minus x squared dA. And then we set it up. I always let y just be the inside one. All right, so this work is going to be equal to y equals x squared up to y equals x. And then the x's go from 0 to 1. Then we get 2y minus x squared dy dx. If you want to try to work this out, it's 1/12. It's just double integral at that point. A lot of these questions for your final or your test, whichever where we're at in your semester, depends on which semester you're in. A lot of it will just be set up. So I will just set it up for you. Or you will set it up for me. You won't even have to do that. Just do the part before it. Right, we're going to get a lot of examples and try to. These are mainly dealing with setups. Okay, so we deal with the curve first. That is a parabola that is upside down. Like this. And then it goes through at 2 and -2. And then the line y equals 0 is right there. So we're dealing with this shape going this way. All right, so I just have to make sure it's not conservative and set it up at the same time. Partial of Q with respect to X, that's Q. We get 1. The partial of P with respect to Y, we're going to get 2Y. So this work over region R is going to be 1 minus 2Y dA. We can set this up now. 1 minus 2y. I like doing y equals 0 to y equals 4 minus x squared. It's usually set up for us. That's why I like doing it. And then x equals -2 to +2. And then dy dx. This ends up being a -352 over 12. 15. Over 15. So like I said, setup is the important part here. All right, let's take a look at the next example. We don't, I think we should build a region, yeah. So we have a circle, that's the x squared plus y squared equals 1. And then they want us to go from -1, 0, that's right here, to 1, 0. So it goes this way. Goes that way. And it has to be counterclockwise. So the circle that's going to be taken is up, right? Going down wouldn't be counterclockwise. This is at 1. All right, so the partial of q with respect to x, this is q, we get 0. Partial of p with respect to y, we get x squared. So the work done will be over the region R. of negative x squared, 0 minus x squared, dA. And then we write this out. Y looks like the better. We get y equals 0 up through, okay, this is y equals the square root of 1 minus x squared. That's solving this for y. And the top part is the positive, so that's why we don't have minus. dy, then dx, and the x's are running from negative 1 to 1. The answer to this, if you want to check your work, is negative pi over 8. Just a few more. You can tell these are pretty straightforward, pretty quick. Before I draw a picture, and I've been drawing the picture first, but I also know what's coming. What you should do, we also know this is enclosed. We actually do. What I was about to say is, it doesn't make sense now. But I always check in my brain or before I write something down, if it's conservative. Because if it's conservative and it's a closed bounded region, I know the answer is 0. So Q of that, with respect to x, I get 6x, nothing there. And then with P, with respect to y, we get 6x. So when I want the work, it's going to be the region of 0, dA, which is 0. So even though we have this circular region, going all the way around, it's going to be 0 because it's conservative. As long as it's a closed path. Okay? If this one, so it's the same process. Right loop of that thing. I don't know if you guys remember what that thing is. If you need to graph anything at any moment, please do. This is I forget how to say it correctly, but so I'll just draw it. It's like that. And it goes in this counter direction. But the problem is it's not a simple loop, right? Because it overlaps itself. So to fix it, what we do is we just do one side, the right loop, and then we have this like over here we're not going to do, right? I guess that's a gross way to put it, but there we go. We only have the right loop of that. I think it's a limnoscape, but I feel weird saying it because I'm not 100% sure. So we got P and Q. So we got partial of Q with respect to X. All right, we get 1 plus 1 over 1 plus X squared. The partial of P with respect to Y is going to be 1 over 1 plus X squared. So that means the work done over region R, we're going to minus those, leaving us with a 1 dA over R. Now, the best way here is to go to polar. We have R is equal to the square root of cosine 2 theta. So I could do the integral from R equals 0 to R equals the square root of cosine 2 theta. So it's what we just solved for there. And then we got 1 times R dr d theta. And then theta is going to go from negative pi over 4 to pi over 4. That's here and there. This answer comes out to be a 1/2. So it's just using polar. The setup is the big thing, using Green's theorem at the beginning. Getting to here is previous skills. All right, moving forward with more curves. All right, so we have find work done through that vector field on the triangle. So I like to draw the triangles. I have 0, 0. I got 1, 0. And I got 0, 1. Along that path. And then it has to be counter for it to work. So we are moving counterclockwise, even though we don't see that manifest anywhere. Just has to be. Partial of Q with respect to X. All right, well, that gets me 2y. Partial of P with respect to Y. All right, we get negative 2y. Be careful here. When I subtract those, I do not get 0. I get 4y. Right, it's 2y minus 2y. dA. All right, then we set up our bounds. Looking here, all right, this line here is y equals negative x plus 1. Has a slope of negative 1, starts at 1. So this goes from y equals 0 to y equals negative x plus 1. And then x's go from 0 to 1 in our graph. For y, dy dx. That's the complete setup. That's what I would ask you to do on a test. So if you want to work it out and see if you can get it, it's 2/3. All right, that is the whole idea for this section. It goes pretty quick. This is a weird chapter because it just gets easier as you go on. I am going to post the rest of this chapter, and it's summed up in like almost a 4-hour lecture if you'd like to watch it, but we don't have time in a summer semester, so we actually end here. If you're in a regular semester, I try to push further than this, so if you're watching this video and you think you're done, you may or may not be. If you're in the summer semester, this is where I stop. So this is it. Please watch these videos, get really good at this. Remember that it will be set up. Most of it, you won't have to do that.